Okay. Is this loud enough?
So I'm your presenter today. I'm Tahseen Shabab.
Right. All right. Hello, everyone. Thank you for your attendance today. The topic of our discussion is TensorFuzz, debugging neural networks with coverage-guided fuzzing. This paper was written by Augustus and Ian Goodfellow. So I'm Tahseen Shabab. I'm your presenter. I've graduated from the University of Waterloo in electrical engineering. And since then, I've been a cybersecurity consultant for firms like IBM, a large bank in Canada, a Fortune 60 telecommunication firm in the US, a North American government, and more. I was also lead developer of a cybersecurity solution called AppScan Source on Cloud, which is used by many Fortune 500 firms. It focuses on application security. So there's a lot of analogies in this paper. Also, I'm the founder of a Waterloo cybersecurity startup, and I'll talk about that more in a bit. Also, today we have our amazing facilitators who have helped me out a lot in constructing this. So we have Susan, she's a data scientist at Bell. Also, we have Serena, she's a senior data scientist at Delphia. So let's give them a big round. So Bibu Labs is a cybersecurity company based out of the University of Waterloo, and we're now regarded as one of the top cybersecurity companies from the region. We've been recently featured alongside Google, IBM, and cybersecurity giants Eastern Tire. Also, we are growing our team. We have a great team at this point. We have our chief scientist, Professor Hassan Khan. He's a PhD and postdoc from Waterloo. His work has been featured by Time magazine. Also, we have Professor Kate Larson as our AI advisor. She's one of the leading reinforcement learning professors from the University of Waterloo, and she recently did some work for DeepMind as well. Also, we have Professor Larry Smith, who's our strategic advisor from the University of Waterloo, who's helping us out a lot. So let's talk about cybersecurity and AI. So cybersecurity and AI has been regarded as a silver bullet for cybersecurity. Recently, BlackBerry closed a massive acquisition. So they bought Cylance, which is an antivirus software leveraging AI to detect attacks. And they bought this company for $1.4 billion. And this is a recent post by the CEO of BlackBerry, talking about the truth of BlackBerry Cylance, talking about how awesome the product is with a very low false positive rate. So their Cylance was definitely one of the largest cybersecurity companies. But unfortunately, just a couple of months back, it took just 2 researchers to fool the AI detection mechanism of Cylance. This is pretty big news. And this is how they did it. So on one hand side, you have the Cylance antivirus, which takes in files, and it basically detects if it's a malware or if it's a good file. Let's call it that. So the researchers were able to look into the logging of the antivirus, and they were able to identify the output of the scoring mechanism, which was basically outputted right on the logs. So now what it enabled them to do was to push in random files and then understand if the file has been detected as a malicious file by the antivirus, or if it's a benign based on the scoring mechanism. So this enabled them to do something which is called dynamic debugging, where you put in files and see how the model behaves. And then using some reverse engineering techniques, the two researchers were basically able to identify the exact model being leveraged. So now they were able to look into the source code and then identify, like there's 7,000 feature vectors used by the model, and then there is some post-processing step, and then you have your neural network. And the interesting thing, there was an additional filter added after the neural network, because when they were training the neural network on malware, there were some corner cases which the neural network wasn't, providing full coverage for, and then they had basically they had a white list and a black list to ensure the false positive rate was lower, which the CEO suggested. So do we have any questions so far? So now what happened was the researchers, once they went through the code for all these models, they were able to identify a bias in the model, in which case there was a small set of a bias, which means that there could be a small set of features which have a huge weight on the outcome of the actual prediction. So what they figured out was the added filter at the right, it was just doing some form of clustering, and the clusters had specific names, and one of the names was a famous online game. So what they did was the researchers added strings from the game's executable on real malware, malicious files or malwares, and they were basically able to bypass the entire system. So this is just 2 months back. So 2 researchers were able to completely bypass a $1 billion acquisition of a company. So the point is, have we seen this before? So this is the new rage within the cybersecurity AI community. But then if we dive deeper into the old work done by researchers, so this is in 2005 and 2004 by Whittle, Meek, and some other researchers. So what they did was they ran an attack against statistical spam filters, in which case it's called a good word attack, in which case certain words which are more prominent within like real emails would have different weights, and then basically what you could do is you can append these good words on real spam, and your spam filter would be full because it adds more weight on words it usually notices in real emails and not on spams. So I mean, it's very analogous to what we just saw within the context of silence. Do we have any questions so far? Awesome. So why are these hard to spot? And here's and on a very high level, this is the reason why we have these blind spots. So on the left-hand side, we know traditional software development, where you have a developer coding in all the logic, so in which case we have full visibility of the logic. But from a machine learning system perspective, developers don't embed the logic themselves, so they only can impact the training data, the feature selection, and certain aspects of the algorithm. And most of the underlying decisions are not known to the developers within the context of a neural network. So let's look at adversarial attacks. So in the context of cybersecurity, we need to understand the nature of the beast. We have hackers who are always looking for the path of least resistance. So on one hand side, if there's a vulnerability, I've been an ethical hacker for some companies. Like if there's a vulnerability and someone deploys a patch, I'll just go for the next vulnerability. It doesn't impact me or bother me as much. So again, I'm always changing my maneuvers as per the situation requires. So one important thing about applying machine learning or even AI within cybersecurity is the data distribution is always manipulated. So in some cases, we can have an assumption that the underlying statistical model within the data would be static, but in our case, that assumption does not hold true. So there are many kinds of attacks which can be performed on systems. So one is data poisoning, which is used. We have seen a lot of these happening in the real world, where hackers strategically insert certain data points, in which case they can shift the decision boundary of your models, and because your models will likely keep on updating based on new training data, and then as these crafted data points get train your model, you kind of shift the decision boundary. So that's one point. But however, this has a huge impact within cybersecurity. So we've seen working with some large companies the following attack. So imagine in a security operations center or within large enterprise clients, you have these analysts. They always look at these attack logs, right? Okay, like they're always bombarded by tons of alerts, right? Could be a false positive, could be a true attack. So now analysts are already bothered by tons of false positives. But then what happens is, if hackers are able to change the decision boundary of your model, then it could insert a flood of false positives, in which case we have something called a denial of service attack, in which case analysts are already bogged down by false positive, but now you have more false positives. But what it does is that it opens up the window for a thing called, for a sophisticated attack, which is depicted here. So what could happen is, while your analysts are already bogged down by false positives, a sophisticated hacker could look at your web config and look at the logs and then kind of do like a sophisticated lateral movement, in which case the deviance from the norm of such a behavior would be negligible compared to the false positives fed by your model, in which case you would be able to easily bypass attacks, bypass detection. And I guess in the machine learning community, this is something we have all seen before. So, it's a specific kind of attack which we call induce specific output, in which case you have your input data, but then just by adding a small amount of noise, which is negligible to the human eye, you're able to basically fool the detection model into thinking that your input is to misclassify the input. So this is now in context of cybersecurity, this is a huge problem because say your analysts have a short amount of time to deflect attacks, and then detecting a deviance of something which is so negligible to the human eye would be very hard. And again, explainability is one of the biggest problems in our industry, and that's like an open problem. Also, in our case, we want to, as hackers, we want to understand the detection mechanism. So there's already tons of techniques where we can pass in data, but get a response from your model, but then we can kind of approximate the decision boundaries. So that's something we already do. But then, as per a research paper, it took this concept to the next level, where you can actually just by submitting different queries to your model and observing the response for neural networks, you can actually identify with pretty good accuracy as to the architecture of the model. In which case, are you using max polling? Is there dropout and whatnot? And also, you can identify training data as well. And the optimization procedures, and these are really beneficial as a hacker, because if I understand this, I know how to craft specific attacks to improve my chances of bypassing your system. So going on a higher level, recently I read this book called Adversary Machine Learning by Joseph and some other professors and researchers. So what it does is that, so this table basically combines all the different techniques a hacker could use, but kind of puts them in certain blocks. So which I thought was very beneficial. And so on one hand side, you have on your axis you have the influence. For instance, you have your causative attacks, and you have your exploratory attacks. So causative is where attackers only have access to both to influence both the training and test data. And on the exploratory side, hackers only have access to influence your test data. And then from a security violation standpoint, you have the different concepts like confidentiality, integrity, and availability. So these are the impacts a hacker could make. And again, the hackers would have different goals. So previously, when we talked about a lot of false positives, we were talking about the integrity of your model. So the goal for a hacker is to embed false positive in your system, in which case an analyst, if they look at tons of alerts, they'll just shut off your detection model, in which case that's a violation of integrity. Availability, again, sorry, I was talking about availability, and then integrity, again, when you have false negatives. But again, like it's you can break down these attacks into different segments. So from that attack standpoint, say if you have tons of false positives, your analyst would obviously turn off your models, in which case that also impacts integrity on a different level. And you have your other domains as well. But for the purpose of our talk from now, we'll move on to the exploratory side, and we'll basically dive deeper and see how TensorFuzz impacts this. So if you don't have any questions, we can move on. So what are exploratory attacks? So against classifiers. So in one case, attackers, for such an attack, attackers don't have access to your training data. They can only impact your test data. And the problem is most of the detection techniques are susceptible to blind spots. And these are the things your attacker would want to look out for. So the question is, how difficult is it for an adversary to identify these blind spots and craft their attacks to leverage them? Which boils down to, how do we identify these blind spots? So one technique by professors from University of Columbia explored the concept of a white box testing. They called it Deep Explorer. So what this model does is that on one hand side, you feed in different inputs, and you have different neural networks. And then what they would do is they would perform some optimization to satisfy two criterions. One is they want to ensure you're activating a large number of neurons between your network, because you want to maximize coverage. And Another is they would want to force a condition where like different neural networks would classify the same input differently. So that's where you have your edge case or corner case. So this diagram does a, yeah.
So for the previous one for Deep Explore, just judging by the figure, is it this specific for images?
So it could be I mean, although this paper I believe was for images, but there could be any kind of input.
Okay, so this is like fairly generalizable.
Yes.
Yeah,
So
okay.
it is. They wanted to make it as generalizable as
Cool.
possible.
Thanks.
So going back to this diagram. So here, as we notice, you have the decision boundary for two different models, but then this is the case where your two models would. Yeah. Yeah. So yeah, so this is your blind spot here, where you have two decision boundaries, but then this is the one which gets which the inference for this would be different for two different models. So these are the cases which this paper, this framework wants to bring out. So another model I was very fascinated about a couple of years ago was Bayesian neural networks. In which case, how do you model the uncertainty of your inference? Now, this is very important in domains like cybersecurity and medicine, where you just don't you act on any inference. We want to understand what's happening in the background, and we want to understand the risk associated with making a decision. So again, with Bayesian neural networks, what happens is you can embed dropouts during your testing phase, in which case we can calculate based on the out. So for one input, and as we change the dropouts and run the same data, we'll have different outputs. So from there, we can identify the variance, which would be your uncertainty. In which case, in this diagram, as if you can see, these are cases where the model is very uncertain, and these are cases where the model is very certain of the output. So which brings us to TensorFuzz. Do we have any questions so far? Okay. So what is TensorFuzz? TensorFuzz is an open source tool, and its objective is to discover errors which occurs only for rare inputs, which is the blind spots we were talking about. So some of the key techniques covered in TensorFuzz is coverage-guided fuzzing, property-based testing, and approximate nearest neighbors. So these are the things we'll dive into, and then we'll kind of combine them to reformulate TensorFuzz. So let's talk about coverage-guided fuzzing. So coverage-guided fuzzing is a technique which is used intensively within the context of application security, where we run these tools and then try to figure out these blind spots and kind of force an application to reach a point where there's a bug. So what we do is first we instrument the program for coverage, in which case basically which allows us the fuzzer to go through the different code execution points, and then we can identify the points where new events occur. So that's on a high level, that's what we do when we instrument. And then what we do is we feed random inputs into the program as we go through the different the branching factors of your application. And then what we do is we continue to mutate the inputs till the point where you get an edge case where the program for some reason behaves differently, and that's what we want to look out for. So how do we identify the coverage of your branches? So AFL, which is a form of which is a tool which leverages coverage-guided fuzzing, what happens is, say for your different, say for instance, you have these inputs, but these could be your branching factors of your application. So it actually records all these branching factors, and then maybe for a different input, it actually does the same thing, but it identifies that, okay, for this input, we were expecting this to happen, but for some reason, there's a deviance, so which could indicate that, okay, this program is acting or misbehaving. And these are the things these tools look up for. Also, with tools like AFL, they look into hit count as well. So for instance, if you look at these coverages, like say how many times did the solution usually go to condition B? Like sometimes maybe usually it goes there twice, but then all of a sudden it starts going there many times. So that's an anomaly, in which case these are the things which this model tools like this would look out for.
Tahseen, can I ask another question? Yeah. So for this image here, so the one is, okay, can you just walk me through it? So there's one input that has one sort of coverage, another input has two coverages, or what is it showing?
This is more for a range. So in which case, what happens is, say you have, like say for instance, when you hit a certain, like say for certain inputs, say for instance, if the input is a hello world, right, a string, and you pass it through your system, usually maybe what would happen is it would go to A, B, C, D, E, and then you have your output, see, on your screen. But then with these counts, what it does, it looks at all the different nodes you hit, but then how many times did you hit them? So in which case, maybe for a certain input, you're constantly hitting the same node, which you're not supposed to. Okay. In which case, that's a deviance from the norm. That's an anomaly. Those are the things we look out for. Yeah. Do you have any? That's a great question. Do you have any other questions? All right. So let's look at the mutation part. So our point was we take in inputs, but we constantly keep on changing these inputs and then feed it through the same application to look for edge cases. So how do we do that? So in the case of AFL, we're using a form of genetic algorithms where we go through a few operations. One is bit flips. So we just keep on changing bits. Also, we add and subtract small integers into the input. And also, we sometimes insert known integers as well. So these are the three ways we mutate the input file. So do we have any questions with regards to coverage-guided fuzzing? Awesome. Then we'll go on to the next part, which is your property-based testing. So property-based testing is a mechanism which is also used extensively within the context of application security, where all we do is say for whatever input we specify a property for the output, right? So this is what we expect from the output of a function. And then what it enables us to do, enables tools like this to do is to basically mutate the input, and then look for cases where we're not meeting the property or the condition of the output we specified. And here are the advantages of using this technique. So one is to cover the scope of all possible inputs. So in which case, usually we leave the input to be whatever unless we specify anything. So in which case, we don't need to bother about it. The tool kind of goes through its own mechanism to identify different inputs to see if we met our properties or the end conditions. Also, in the event of a failure, such techniques usually identify the exact case where the property is not met. So in which case, if you keep on adding different strings and all of a sudden to your input, and then all of a sudden your output behaves in a different manner, then it will actually output the exact deviance or the exact delta or that end string which kind of disregarded your model. And they're also easy to reproduce and replay. So these are some of the advantages of using this.
Could you go through a quick example for the last slide?
Yeah.
So for example, abides by properties. So is it like if it takes in string types as inputs, like do they only have to be string types?
So it could be like usually with these models, the input, unless we define the input, like it can be left to be whatever. But then the condition for this technique is the output. So we just define the output, and the thing does what it does. But usually, usually with these techniques, for the first input, usually we want to define it as something which is valid, but then you let it do whatever. So usually we want to define something which is valid, because then you get maximum coverage, or else it's going to keep on hitting an input which might be valid, and then it's just going to take forever. Yeah.
So it's not like to purposely just like put in like a type that's not intended, but rather kind of like to maybe put in at first the type that is okay to be fed into.
Exactly. So that's what we would ideally like to do. And say in the application security world, what we do is when we try to hack into a system, or when we set up these scanners, what we do is for the first round we actually put in real digits, but then we don't have to tell this tool how to keep on mimicking the how to mutate the input. So it's going to do whatever it will.
I see. So start with like an okay input, and then after that it just goes off by itself and mutates, and then it could mutate into something that's not.
Exactly. So that's how this technique works. Yeah. Do you have any? That's a great question. Do we have any other questions? All right. Did that answer your question? All right. Cool. Yeah.
So the question is, when do you know to stop flipping the bits, adding, subtracting, etc.?
So is it with regards to property-based testing?
I think so.
Yeah. So if that is true, it's usually when you're.
I think it maybe they asked it a little bit earlier when you were on the mutate slide. Maybe go forward.
So
forward.
Okay.
Never mind.
Yeah, here.
This one, yeah.
Okay, so
Yeah.
so that's a good question. Well, in essence, what happens is you don't stop mutating, but the point is, say you we want to identify, we want to hit, say for instance, usually with these fuzzers you have an objective function. The objective function is what do you want, what's the desired output. Maybe it's a misclassification or misbehavior, right? So usually you keep on mutating till the point where you hit that objective function. It could be like a huge deviance, or it could be specific errors which you're looking for, and in that case those are the things which get logged for further analysis. Yeah. Okay. That's a good question. Also, if you don't have any questions with regards to property-based testing, we can next look into approximate. Yeah.
Well, in the reproducible part, does it makes it a requirement for the program you're testing must be pure functions? That means no external state dependency and no random output.
So if I get your question, it's so with regards to these functions, are these only internal functions and not external dependencies?
Yeah, with deterministic output.
So,
and does not depend on external type and has no side effect.
Okay, so I can give you an example from the real world. Usually we treat these application as a black box. So again, we don't usually, this is a black box, here's a function, or it could be an API call, we pass in whatever input, but we expect this output, so it's a black box.
Yeah, but if it depends on some other bit that is really far from the from that snippet of program itself, then you have to change that part to observe the effect.
Could you kind of repeat that?
For example, if you have a global variable that is defined in a different file.
So if you have a global variable,
yeah.
All right, yeah,
and then the problem only manifests if that global variable is set to some specific value, but that part is not available to a debugger.
So in that case, that would be a bug, but then you'll have to reproduce it yourself. If it's some edge case, then you can rerun the application again till the point where you hit that. But then those are the then you'll know that for this input, this is the.
Is the fuzzer supposed to?
So this is not fuzzing though. This is property-based testing.
Okay.
Oh.
Yeah, so we'll get there. Yeah.
Sorry.
Because this is for neural networks, so obviously.
But that's a good question. Maybe we can target that during the discussion stage. So I would love to have that conversation. Yeah. So approximate nearest neighbors. So that's the third topic for TensorFuzz. So approximate nearest neighbors, pretty simple. Say you have a query point, and then you have these different different points. So we want to identify what's the with nearest neighbor. We want to identify what's the point which is closest to your query point, and then with approximate nearest neighbors, we kind of loosen up the condition where we want the closest point from your query point, which satisfies a certain criteria. All right, so now that we covered all these different points, the problem is coverage-guided fuzzing does not really work with neural networks. And here's why. So with traditional software workflows, you have your inputs, but then you have, for coverage metrics, you can have different lines of code executed or which branches were taken, were followed by your application. So that's something we can do for traditional softwares. But the problem is within the context of neural network, this is really hard to do. Because again, the software implementation may contain, many branches, and these branches are more dependent on the architecture of your system. So with the same input, you could have various different outputs while the branching factor is still the same. So that's one of the challenges of applying coverage-guided fuzzing within neural networks. All right, so how does TensorFuzz work? So let's dive in. So on one hand side, so this is the architecture of TensorFuzz. So you have your neural network, and instead of like with traditional coverage-guided fuzzing, you have your application code. But in this case, we feed in the TensorFlow graph, and so that's our input. I mean, that's the core model we want to test. And then for our seed corpus or for our input, we put in valid neural network inputs as opposed to tons of arrays of bytes, which usually fuzzing would do. And again, we do this because we want to ensure the model you're actually running the model running appropriate. You're covering a decent amount of your network. And then we have the input chooser, and what this does is it intelligently chooses your inputs and feeds it into your mutator. Now, the intelligence comes into play because based on the intuition that whenever we have these, whenever we add these inputs, like you have a bunch of, say, your input data, but they keep on increasing as you find new paths, so which we'll talk about, but then what this input chooser does is that it looks at the input corpus, but it adds more weight on the most recent ones, because as you cover more ground, then maybe there's an interesting input which gives you that added visibility. So that gets appended into your input corpus. And from a fuzzing standpoint, it's better for us to use the newest input, because perhaps that could be more valuable as we pass on. So that's the intuition behind this. Do we have any questions here? Yeah.
What is the vocabulary here? So in the
previous
sorry,
one.
Go back to what is the vocabulary?
So this example was in the So this example here is in the context of, say, a text. Say the vocabulary would be, say you have an input, like you trained your model with certain text, right? So I mean, the input in that case would be, like a certain string from the input corpus. So it's a valid training.
Yeah, just to clarify even further, this method TensorFuzz, you can use it for images, so like neural networks for images or for text, doesn't matter. Previous works were more specific to one sort of application of neural networks, which is why this is more special, because it's more generalizable.
Great. Do we have any other questions? All right. So if you don't have any questions with regards to how the input chooser chooses the input, then we can move on to the next slide. So then we have the mutator. So again, on a high level, you have a seed corpus, and then your input chooser chooses the input intelligently, adding more weight to the newest data points, which gets embedded. And then what the mutator does is, again, like similar to coverage-guided fuzzing, you kind of change the input strings or the input data and then feed it into the network. So again, it's pretty similar from a text input standpoint. Again, we use this a similar policy where we either add, delete, or subtract characters, or random. Basically, what we do is we add, delete, or subtract characters based out of like a random distribution. So what happens next is, again, you have these mutated data points, and then we feed it into the network and we observe the output. So that's on what happens on a very high level. And here we try to look for two different outputs from the neural network. One is your coverage arrays, which kind of defines like the different coverage paths of your neural network, which we'll talk about in the next slide. Also, what it does is that it also feeds this metadata array, which is pretty much the output of your model, and we analyze the output to identify if the objective function has been met, in which case, did we get a crash or whatever was defined by the objective function. So again, we feed in mutated data into the neural network, and then there's two outputs we look out for. One is your coverage array, which identifies how well we're able to cover the different points of your network. And also the metadata array, which what it does is, again, we're looking to identify the real output of the model that we hit the objective function. Sorry? Do you have a question? Okay. So a crash is just an example. It could be many different things. Say, for instance, in one of our examples, we look out for nans. So that's in the experimentation section. It could be misclassification. It could be, yeah. So again, it's defined as per the objective. It could be like certain outputs, like undefined outputs could be, or like outputs which are not within a certain range. Yeah. This is from the paper. Again, like crash is it's just an example here. Yeah. Did that answer your question? So the experimentation section would actually dive deeper into certain examples. Also, let's look at the coverage analyzer. So core part of our product, again, is to of TensorFuzz is to identify if we actually how deep did we cover the entire network. And so the next slide actually dives deeper into this. So that the objective is, okay, how do we know that we covered as much of the network as possible? So looking at some of the desired properties of a coverage analyzer. So one is we want to identify if we hit a new state within the network. So in which case is there something we previously didn't look into within the network which we want to identify. Another is this coverage analyzer should be fast. That's an ideal property we want. Also, we want to remove manual intervention as much as possible so that this coverage analyzer generalizes to different models, which Serena was talking about. Also, another thing is exercising all the coverage should be hard, in which case, say, for instance, if you have inputs for which you already go through all different depths, then this technique will not be wouldn't add much value, because our point is we want to identify those areas where it's very hard to penetrate, but you're getting, then we fuzz on top of it. Yes?
Oh, so there was a good point made by someone in the audience earlier. So, for example, for traditional CGF, some of the metrics might be, lines of code covered or stuff like that. But and in the paper they mentioned several different types of potential metrics. So in this particular, like in TensorFuzz, is there a particular metric that they use, or is that coming up?
So that's a great question. So the next slide we'll talk about that. Yes. Yes, that's a great question.
Question about this slide. So the exercising the full coverage should be hard is a necessary condition for it to be meaningful.
Yes.
Is there any reason why it is the right direction to go? It is of course necessary, but is there any suggestion why it should be the right way.
Yes. So, imagine, let's look at it from an application security, like traditional application, right? So for a traditional application, you have these branches, right? Say, for instance, branches. So if an analyzer, and think about these branches as depth, right? So high resolution, right? So now the more branches you have, the more depth of your image, in which case now whenever we run a scan, we can kind of look at all the different bits and pieces, the tree moving, in different directions. So that's one analogy. But if that depth wasn't there, in which case, with one input you're getting, you're covering all the, depth, then you can't really branch into further cases. In which case, again, you won't get that depth, and without that depth, your fuzzing wouldn't be much of value. So the point is, again, like having like these like that. The point is for the analyzer to actually, be in a place where it actually can find the most depth, as much depth as possible. Did that? So I can go. I think the next slide would actually add to that. I think we have images coming up. Then I can kind of dive deeper into why you need that depth, or why. Because think about it. Think about the depth as different conditions, but then basically as you add in input, then you're like you want cases where they're hard to find, right? And then you keep on analyzing, and then through different iterations, then you have one point, and then you add in different input to kind of break it into others.
But it really depends on the input.
In our case, from an application security standpoint, it is based on the input, and it's based on certain states as well as defined. But from a neural network standpoint, it's not entirely based on input, because again, you have the architecture, right? It's based on the architecture as well, which is why this tool actually proposes a very different way to identify the coverage. Yeah. Maybe the facilitators can add to your question.
I think if you think of it, so TensorFuzz is trying to kind of like find inputs that break the neural network. I'm borrowing that from Susan, breaking the neural network. So if it's easy to cover all possible cases right at the beginning, you're not going to be able to see those inputs that break the neural network. You'll just run it and it'll be done. So making it difficult to cover forces the method to try a whole bunch of different inputs and hopefully find those edge cases. That's sort of how I think of it.
Yeah, I think one point it brought up is that it's not necessarily trying to break, like, for example, the code or the software itself, but rather like trying to be able to run it through the neural network, at least at first. Like, it's not just trying to just like break the code, or let's say it's running on a website, like it's not trying to break the website. The focus is on the network itself. If that.
Does that kind of make it more clear or not really?
Yeah, well, my point was that there are many things that are hard. Some of them are just useless. So by making something hard, I don't guarantee the utility and any value in it. So I wonder what is the clue for the usefulness of that? Is there like anything besides that? Yeah.
So the objective here is actually coverage, but maybe within the next couple of slides we can because the interesting thing is the way we find coverage with regards to TensorFuzz is a bit different, but I mean, perhaps like the next couple of slides I can talk about that with the images.
Yeah, and if it doesn't clear up, we can talk about that idea of hard versus useful in the discussion.
Awesome. So again, with regards to TensorFuzz, we're using fast approximate nearest neighbors to identify the coverage aspect. So in which case, what we do is what it does is that it looks at the activations of your different say for different inputs, it looks at your activation vector, and then it kind of does an analysis on your activation vector to identify if a new coverage has been identified. But the next slide actually has a visual depiction of it. So what happens is basically, say you have your input, and then there's a certain activation vector we look out for, and then what we do is we look at the activation vector, and then we look at the activation vector for when we passed in old inputs as well. So then we do a delta analysis, which is we use nearest neighbors to identify if the deviation from the activation between the two say two different instances surpassed a certain threshold. So that's how we identify, and this is in essence this is the depth. Now if yeah.
So activation is basically all the activations of all neurons in all of the layers, basically as a vector, right?
So it could be that, but like the paper suggests that even the last two layers, the activation vectors from the last two layers still gives a decent result.
Okay.
Yeah. So going back to your point, I mean, I guess this is where the hardness comes in, because this is our coverage. So in which case, if you for one input, if you already surpass this, right, and then you keep on adding more inputs, but then the deviance is not as high, in which case you're still stuck in the, so you can't model that depth. That's how I understand it. So it's more about, say, like we need to identify these cases where, we are recording all the deviances, and then and then we identify new cases. So I guess the model has to identify the ideal solution, which TensorFuzz uses approximate nearest neighbor, but then this technique should ideally be able to define the different depths of your model. I mean, that's how I understand it. Yeah. Do you have any questions? Any further questions? Yeah.
Can you go back to the algorithm? Can you go back to the algorithm? Sorry, the nearest neighbor algorithm. The one that has the nearest neighbor.
Approximate nearest neighbor?
Back.
That's, yeah, one more, yeah.
This one?
I forgot.
No, the one
with the figure,
with the bubble,
the one
yeah.
that shows like the distance measure.
Okay.
Oh, yeah.
So it's this one, yeah.
Oh, this one?
Not this one.
No, keep on going back.
Approximate nearest neighbor.
Keep going, keep on going, keep on going, keep on going.
Wait.
Oh, wait, what?
Wait, what?
It was before
Oh, wait,
that.
it was,
It was
yeah, keep
Okay,
going back.
I'm just going to ask
Keep
my
going
question.
back, keep going.
So my question is,
Keep going. One more.
I may miss this part, but
Yeah, this one.
This one.
when you're doing nearest neighbor,
Yeah.
that is assume you already have a set of points. But I thought the point about fuzzing is that you kind of generate random inputs, right?
So that's a good question. So the point is, here again, this has nothing to do with the inputs. It has to do with the activation. In which case you have an input, but then you're looking at the activation vector, and then you're doing an analysis on that.
But you start with the real data. You start with the corpus that it already exists,
Okay.
and then you get like initial set of activations,
Okay.
and then you start mutating.
You start doing, okay.
Yeah. When you start mutating, you already have some activations in the activation space.
Okay. But when it says find closest point, like that point, is that generated, or is that still from the data set?
So the closest point I can is actually from, for instance, if you look at this graph. So that's a good question. So the closest point would be from the activation vector of your past, say, occurrence where you had a different input,
okay.
and then you're doing delta analysis between a previous state and the current state to identify, hey, is there a case where the delta between your activation vector surpasses a certain threshold?
Oh, thank you.
Yeah. Do you want?
It seems like, is this done online? Like as your fuzzy, your coverage analyzer keeps going on, you compare the current input to every other old input, or do you select from your old inputs?
So these are things which are kept stored, and then from my understanding, this is stored, and then once you have a new input, you can do a delta analysis, and it has to be in real time because again, in order for or it could be stored and then in some kind of stack and then went forward, because we want to identify edge cases, and then we want to dive deeper into those edge cases, and then kind of dive deeper and deeper. It's kind of like, say, if you, for instance, from an application standpoint, if you have different functions, all of a sudden you hit a new area. Now we want to really explore that area and see what else we can find. And I guess it goes back to the point where, say, when we mentioned like we intelligently select inputs. So here we talked about how once we find new inputs, we kind of add more weight to the new inputs, because again, as you've identified, say perhaps the new input would give us a certain coverage, but now we want to add more weight to that and see what else we can do pivoting of that. Yeah. Do we have any other questions? Yes.
So before the network outputs two things, coverage arrays, and the second thing is like the metadata array. So is coverage array the same as activations?
Pretty much, yeah.
And what is the metadata?
So we can. So the metadata would be like the output, and it could be the end result. Could be your inference. It could be more, but then maybe the examples would be better. It's just how you're tuning it to your model.
Is that clear? In the experiment section, we'll go through two like concrete examples, so it'll make it a bit more clear. But if it's not clear, ask your question again.
No, if it's gonna, like, maybe after.
So in our case, it would be your output, for instance. Like it could be what's the inference? Like what's
or like
the
if
weight?
you're doing classification, metadata would be like a 4 if the model says the image is a 4, like that.
Yeah, exactly, with the percentages. And, yeah. Cool. So if we don't have any questions on this slide, we can dive deeper into how the coverage analyzer works. So here are the details of your coverage analyzer. So on one side, when there's a new activation vector, so what we do is we use the approximate nearest neighbor algorithm, and we look at the nearest points which got triggered for past instances, as we've identified here. And from there on, we look at the distance between the two different activations. Like one is current, one was from a different times with a different timestamp. And then we basically deduce the Euclidean distance between the two, and if it matches, bypasses a certain threshold, then we add the new input to the corpus, which has more weight, as we have identified. So this is going to be your input, which would get added to your corpus, and now whenever new data points are added to your mutator, this would it would have more precedence. Like the new data would have more weight. Yeah.
So a question of clarification. So it's not essential that the nearest neighbor, finding the nearest neighbor is not essential. It is essential to guarantee that we are far away.
Yes.
Right?
And the paper talks about this as well. Like, I mean, you don't need the nearest neighbor. Yeah.
Can I ask?
Yes.
So I have a question, like, is coverage a function of a single activation, or is it a function of a set of activations?
So although it's a function of a set of activations, but then this paper states that if you only look at the last two, you get a decent like a result. So that's
what I mean is, like, when we calculate coverage, do we just need one input and one basically point in the activation space, or we have the set of inputs that maximize the coverage in that, like, vector space?
So in this context, it's one input. And then, like, you have multiple, you have an activation vector, and then, but then it looks at the one input.
So basically, okay, yeah.
It relies on having a number of old inputs.
Yeah, that's what I was asking. Yeah.
So I think what you're looking for is it's not a function of just a single activation.
Yeah, that's what. Yeah.
That's a good point. In application security, it's a bit different. Say when you have your application, because if you have a sequence of events which brings you to a certain page, for instance, and now you're adding different things. So that's a bit different. In this case, again, you have the one input, but then we keep track of the activations for prior instances, and when we do a delta analysis or the nearest neighbor algorithm. Did that answer your question?
Is there a functionality in the framework to suggest how many layers you should be looking at? Because if you're just looking at the entire activations for something like for a very, very large image detection network, it's a lot of memory.
So this paper talks about, if you look at the last two layers, apparently you get a pretty good result. This is what this paper suggests. So we don't need to look at all the different activations. We just need to look at the ones for the last two layers. But this is as per this paper. I haven't done any experimentation on top of it, but maybe, or I don't know if you too.
I think it would be interesting to talk about that, but let's talk about it in the discussion because I think we're really close to the break.
Okay.
Yeah, but try to remember that question.
All right. Do you have any more questions? That's a great question. We can talk about it during the discussion point. All right. So this is the last point. Again, often good results are achieved only by looking at the last two layers. All right. So again, going back, so we just talked about the different objective functions. We also talked about how we understand coverage. Again, with the objective function, we look at the output and to identify if there's a certain criteria which has been defined by the objective function. So then what happens is once this function is once we pass this state, we want to append the data back, like the new data coverage point. So one is so again, it's added the data, the input, the mutated input, which gave us some interesting findings, are treated in certain manners. For instance, it's added to our corpus. If new coverage is achieved, and again, this is the one which would have more weight once we roll back into, like selected, once it's selected by the input chooser and goes back into the model. Another is it's added to a list of test cases if the objective function is satisfied. So again, say if there's a certain condition you're looking out for, and if that has been met, then we add that within the test cases, and later we can do further analysis on top of them. And we're on the break now. Thank you.
Okay, so 5-minute break. Go and eat some pizza. I think there's a lot left. And then
Let's look at the experiments. So one is finding NAND. I don't know if this is how you guys pronounce it in the machine learning world. NANs, all right. NANs.
Okay, so everybody says NANs except for me.
All right. All right. So NANs. So again, NANs are hard, like cause trouble for many researchers, and they're hard to track down. And again, like in the context of the paper, they embedded a bad loss function. This is just as a form of fault injection into the network, and then they wanted to see how TensorFuzz performs at finding these NANs. Yeah.
So this wouldn't necessarily help you find where the fault in your code is, but just let you know that there is a fault?
Yeah. So from my understanding, it would be the input, and then it's going to find that, okay, for this input, you're getting the NANs. In which case, in this experiment too, you have, this is the input which caused the problem. That's my understanding. Yeah.
Oh yeah. Yeah, I wanted to say the same. Yes. Sorry.
Yeah, but it's the input.
I guess just to like paraphrase what I understand it as is like it's not like not every experiment is about like let's say finding NANs or even just like finding an error, but and not telling you where it is, but just like for this particular one, they just want to see what kind of inputs could be causing NANs, right?
Yes.
Or because like if you wanted to not have NANs, you could like hard code that into the code somewhere. Right? Is it just trying to see like what is faster at finding out which inputs can cause NANs? It's faster than a baseline kind of like random input generator.
Yeah, that's my understanding. Again, it boils down to the objective function as well, in which case they're looking to look for NANs, in which case fuzzing kind of identifies those cases where you generate the NANs. Mm-hmm. Yeah.
Yeah, because I'm thinking of like in a practical case, like if my neural network output NANs, I would probably just like code something to like turn it into 0. So like yeah. Anyway, go on.
Do we have any other questions?
There's one online, but it's not for this section. It's from the previous section.
Okay.
I don't know which slides she's referring to, but the question is, anything further than L is not covered. Wouldn't it be better if you know L already, simply reduce the coverage from L on? The letter L.
Is that the nearest neighbor?
Yes. So what's the question?
Okay, the question is, anything further than L is not covered? Question mark. Like, is anything further than L not covered?
So the point is, once the distance is beyond a certain L, we like. So what we do is I have a slide for this. So what we do is we check the Euclidean distance between your activations, and then we add the input to the corpus if the distance is greater than L. So this is a tuning parameter. In which case, if it's beyond L, then we add it into the corpus. Yes. Was that the question? So again, when you have different.
Wouldn't it be better if you know L already, simply reduce the coverage from L on?
So L is a parameter we state. It's a tuning parameter. So we already know L. We kind of define that. It's something we can play around with.
Okay.
I guess would you say that L is kind of like how fast you want the corpus to maybe expand, or like how different the corpus change? Well, like the outputs change before it's added to the corpus. Like if L is very small, then maybe like every small change will be added to the corpus. But then if L is very large, then it has to be a very, very different output before it's added to the corpus, right?
Yeah.
Yes.
Yeah.
Good explanation. Did that answer the person's question?
I
think it was
seems
good,
like
yeah.
the question, like maybe there's misunderstanding what L does.
Yeah,
in
yeah,
the question.
yeah, that's why we
It says like that.
So the point Susan suggested was, say, if you have a larger, like a smaller L, then you're more sensitive, and in which case you keep on embedding more and more inputs to the corpus, and then you keep on mutating those inputs, and then you kind of have a higher coverage. In which case, I guess L is directly proportional to the how hard it is for your model to kind of look at the different branches, in which case it might tie into the conversation, the question that was previously asked as well. So for instance, you have your L, right? If your L is small, if your L is hard to achieve, in which case, you keep on, trying out, experimenting different values, and as you have more values, you can find these interesting input points which would give you, like certain outputs, and then I guess you're improving your, like your test cases, because now you keep on iterating on the inputs. So again, the hardness has a correlation with the length we define, from my understanding. Yeah.
So you're saying that you might lose some sort of like outputs?
Yeah. So the interesting thing is, again, so if the L is too big, then you keep on trying, right? In which case you keep on mutating. So the input change.
Improving the input, right? So you're just losing those cases.
So when let's talk about it. So when the L is large, right? So let's think about it. So when the L is large, right? So now you I see what you mean. Like, so when the L is large, then you keep on trying more combinations till the point where you reach that state. But when the L is small, but then little deviations would get added and then mutated.
It's to changing a step size or the learning rate. Maybe there are some trade-offs.
Yes.
Actually, little deviations won't be added just because they are not sufficiently large, right?
So yeah. So when L is large, again, you're right. But you keep on experimenting, but they don't get added. But then they get added once you reach that state. But when your L is small, in which case what would happen is that they would get added sooner. But then you kind of break down from there. Yeah. Interesting. Okay. So here on the left-hand side, so this is the results for finding nans. On the left-hand side, we look at the coverage over time for 10 different random restarts. And again, so on the right-hand side, we identify an example for which there's nans. Again, you have the coverage here where again, like there are cases where you have, we try in a lot, large number of inputs to get the maximum coverage. Yes.
Does it handle network architecture with variable, with dynamic output as well? Like it has a dynamic computation graph at the end of the network, which determines the size of its output.
So I haven't tested on top of it, but we can definitely think about it if our facilitators want to take that. If not, I can give you an answer based on my understanding. All right. So the question is, if you have an input, but then you have dynamic output, so maybe there's something which happens in the background for the same input you're getting different outputs. Is that what you're stating? For the same input, you're getting different outputs.
Yeah. So you can't measure the Euclidean distance directly.
Yes, but then there will be cases.
He's talking about differently sized outputs. So you might have a different number of neurons in your activation layer.
then how are you going to measure the distance?
But yeah, that's his question.
So you're saying here is, say for instance, you have like your.
If somehow the neural network is dynamic and the number of neurons in the activation layer can change. Is that what you're asking?
Yeah, exactly. Good. Really good.
That's a good question. That the paper doesn't talk about it, but maybe we can take it. We can come up with some intuitive answers.
Yeah, we can discuss it now.
Yeah,
Everyone's
so that's a
interested,
good question. Yeah.
So I wonder what is the implementation of such dynamic network. Probably there is some space within each particular case is a subset, so that you can. There is a space in which all the possibilities are embedded, and you can somehow compute leading distance in there. No. How?
Yeah. Well, I would think that the nearest neighbors only really makes sense if there's a fixed size to the activation vectors. Maybe you could try replacing nearest neighbors with a different algorithm for testing that, if you wanted specifically to have dynamically sized outputs.
Was it mentioned in the paper?
No.
No.
Okay.
And the paper even says if you have a case where you have one input that gives two different outputs that increase the coverage, they just add that input twice to the corpus. So they take a naive approach to something like that, if that helps. Even though that's not really what you're talking about, but yeah.
Yeah. So.
Yeah.
Okay. All right. That's a great question. In the context of application security, these are easier to find because again you have these branches, and then for certain inputs you're getting from a certain branch point based on the instrumentation you're getting a new maybe now you're calling a different API or whatnot. In which case those are things which we can identify.
Sorry, I'll just be blunt. So far, I didn't see a relationship between this and cybersecurity.
In application security, these techniques are based directly from application security. For instance, with code, like what you're doing is you're doing a coverage, right? Like for instance, your code coverage, right? So here you're covering the different paths you can take from neural network standpoint, and in application security, it's the coverage metric could be the different like functions you're calling or the number of times you're calling those functions. So again, the objective here is how do you identify that a new state within your.
What I observed so far is that it only uses the state of the last several layers, while ignore everything in between.
You don't have to. I mean, in essence, you can like the results are performed pretty well with the last few layers, but then. The interesting thing is, like, say, going back to this one slide, which kind of goes through this. See, again, I think this is the slide. This is the difference. Like, this is the analogy between the two. So one is with traditional software, the coverage metric is identified with lines of code and which branches were covered. In the context of neural networks, what happens is for the same inputs. Like different inputs will often execute the same lines of code or the same branches. But again, like with different inputs, you can still get the same result. So it's more based on the architecture.
Do you think it's kind of a simpler case?
Similar?
Simpler.
Like
the number of state is, it's much easier to measure comparing to a traditional program that has many branching conditions.
It could be again the novel the question it could be simpler, it could be different, harder as well. So it depends on how you look at from a context of an application security, you can do instrumentation to identify these these different cases within your code. From a neural network standpoint, like the point is how do you identify this coverage was one of the biggest challenges for this paper, and where they've identified with your nearest neighbor algorithm, you're able to identify the coverage and then keep on adding more inputs in order to identify edge cases. So that, I mean, with application security, this has been, like, fuzzing has been there for the longest time. So I guess there was more time to do thorough research analysis, and tools like AFL work really well. From a neural network standpoint, this is something new within, and like the way in which coverage you're identifying or recording coverage has been, the way in which proposed by this tool is novel. Now, easy or hard is, I mean, like you have analogies. It depends from, you know, how you look at it. So what's your definition of hard? Like, that's
my perception is that the traditional program resembles a very dynamic computation graph. A case that is like, you know, that is not discussed in this paper at all.
Yes.
So it's inherently harder. That's just what I thought.
It is hard, but then you have these tools which do a great job. Again, by hard, I mean, it just takes longer, right? I mean, these tools like AFL, you usually, I mean, you can run distributed systems, and then you're basically parallelizing your process and then finding these cases. So they run over various iterations, right? So again, the algorithms are there. It's just you have fuzzers running in the background for a long time, and then over time it identifies these edge cases. So again, from a hard standpoint, the algorithm is there. It's just you keep on running them, like, you know, over time as the input mutates. So
I wasn't quite listening.
yeah.
I think it's not a question of hard or easy. Like, it might be harder, but we just have had more time to come up with algorithms for it. But this one, it's just new. You just have to come up with a new algorithm. It might be harder or easier. But that's not the question. The question is, do we know how to deal with this type of problem?
Yeah, well, that's basically, yeah.
Well, that's a great point. Maybe this looks easier, but again, the novelty of this paper is, okay, how do you identify, you know, how do you maximize coverage? In which case, they're using the nearest neighbor algorithm. Yeah.
So maybe we can discuss more in the discussion point.
Yeah, but that's a good question. All right, so if we don't have any questions from this example, we can move on to the next example. Is there a question?
I have a question.
Yes, go for it.
Okay, I want to try. Okay, so is this whole experiment is on the premise that you have to fix the randomness or the seed of the initialization of your weights? Otherwise, you get a random result every time you rerun the network, rerun the training.
It's probably pre-trained network. Yeah, it's fixed.
Oh, it's
the weights are
okay.
fixed.
Okay.
All right, cool. So we can look at the next example again, which talks about quantization errors. So again, many times we have these models, but we quantize these networks. How do we ensure our results are accurate? But so in which case, as per the experimentation done on this paper, fuzzing provides a.
Can you just clarify what quantize is, because I'm worried that it might not be clear to everyone.
Okay, so from my understanding, again, you have a model, but then you kind of bring it down into a smaller form, which you can say deploy within like a mobile phone or something. Yeah, awesome. So again, from a quantization standpoint, we want to understand, like you say, if you have a subset of like a smaller version of a model which you deploy in like a mobile application, we want to understand if there's a delta between the real network which was used but then you have the smaller version of the model. And then, so in which case, fuzzing, again, from this, as per this paper, fuzzing provides a great way to solve this problem. And then say on the left-hand side, you have, again, coverage over time. So for 10 different random restarts. And then on the right-hand side, you have an image which is misclassified, where there's a delta between the classification of the real model and the quantized model. So that's here. And the interesting thing is, this paper says that there were 3 failed attempts. I'm not sure exactly why that's the case, but that's something noted on the paper. Hasn't been elaborated on. Yeah.
Well, they were running the network for many iterations, many mutations, but they had a cap for the number they were going to try. It's 400,000. And in a number of these trials, they never found a mutated input which was incorrectly classified. So the 3 that reach all the way to 400,000 is interesting.
But it says that there were 3. Oh, so I see what you mean. So they wasn't able to even identify them. Okay, interesting. Yeah, it's a good point. Do we have any more points here? So if we don't have any further questions, we can move on to discussion points.
Do you have a question?
Yeah, regarding the last slide, could you give more details about how do they model the quantized and the original neural network? So do they model the original neural network on the computer? Do they use long arithmetics or something else?
Maybe we can ask that question to the facilitators. I didn't see that information on the paper.
They don't really give that information.
Okay.
Yeah.
I think they said they went from 32-bit to 16-bit numbers.
Yeah.
And
So 16-bit is quantized, 32 is the original.
That's right.
Yeah, so I have a question. In a regular neural network, from my understanding, that when you get n to n, it's just an infinite number, right? Or if it's the value that's too large?
No,
There are probably many reasons.
Oh, okay, so it's not because it's a very large value.
it could be, but there are other cases as well.
It could be
So
1 over 0. It could be infinity over infinity or infinity minus infinity or something like that.
Because I was thinking if you batch normalize it, but I guess that wouldn't solve the 1 over 0.
Maybe the facilitators could. Yeah. Okay. Cool. Right. So we can move on to discussion section. So I mean, one point is so after all this, how do we embed security into machine learning solution development lifecycle? So that's a discussion point we can have.
Okay, so first of all, TensorFuzz is open source, so anybody who wants to embed security testing into your machine learning solution development, you can easily do that. But I'm curious if anybody actually actively does this in their work. Is security something that's sort of left to the security engineers, or as data scientists, machine learning practitioners, do you actually care about this? Anybody? No one cares.
I guess it depends on the type of problem that you're solving, right? There's some machine learning, the data that you can't really generate yourself and you can't really fake it. We'll take SoftBuy as an example, right? The data that we're doing with SoftBuy merchants data, you can't just fake buying some stuff and having random customers. So those data is very hard to randomly generate. And for those cases, I don't see a hard push for security testing. But if the input is user input that you can just randomly generate, I can see this will be something that you want to integrate in the system, right?
So it's a great point. It depends on the context of the problem you're trying to solve. So I mean, so in security-sensitive domains, usually many times we use different models as well. So in which case, if somehow a hacker has some understanding of one model and tries to mimic them, but then the inference is generated from different models, so in which case the end result would be still a combination of multiple models. So again, it makes it harder for a hacker to really penetrate such a system. So that's something which is done. Again, this is a very new topic within the context of cybersecurity in general as well. So there are cases like what I'm interested in. Again, I'm looking at it from an explainable inference standpoint. So are there ways for us to come up with some explanations as to why certain decisions are made? So perhaps that gives us an understanding of, we can look at it from an end standpoint and go for the input. So having explainable inference would be really helpful for us in our industry. And this is one of the active challenges within I believe the machine learning community as well as within the cybersecurity community as well.
I guess like in the context of like the antivirus example, like for example, like if you want to fool a network that is, let's say, classifying something, then being able to know what could fool that could have real implications on like real implications, I guess, like fooling something, or maybe like in terms of like image classification, like if you can fool, I'm not sure like what exactly, maybe you have more examples, like maybe a website that is supposed to check whether this person is really this person for security reasons or something like that. Like something that has real implications, then involving something like TensorFuzz in your development process. Like let's say I was developing an application that could tell if this picture is actually of person A, then like I'd want to test it, right? Like I'd really actually want to see what can fool my network, and there would be real implications.
Absolutely, that's one approach. Like another could be, for instance, Bayesian neural networks. If there's an element of uncertainty, we can identify, and then maybe we use some form of active learning to identify those cases where we're uncertain, and then have a human in the loop to kind of look at that. So that's at least one way in which you're mitigating risks, having someone to look at those cases. So that's one approach.
Yeah, but I guess like what Serena mentioned before when she was asking everyone like do testing like this, I guess like let's say, well, if I'm working on like a recommender system, like what am I gonna care that, let's say, you can fool the network that you love cats? Like I don't care too much about that. It's okay, I guess.
Yeah, it depends on the context again. So in machine learning, so so if you have a model to detect attacks within cybersecurity, you'll have people trying to bypass that. Same applies, say, if you're running a neural network within, say, an autonomous vehicle, for instance, that's a high impact situation. Same applies within the context of healthcare as well, where those are the cases where we really want to first focus on. Again, at the end of the day, cybersecurity is all dependent on risk, like what's the risk, right? And what's the reward for investing in certain solutions to mitigate that risk.
Is there any reference on, going back to the explainable neural network thing, is there any reference on the success of using this technique to explain the network better?
So from an explainable inference standpoint, that's a problem in the industry because on one hand side, you have analysts and they have a short amount of time to deflect attacks. So again, they'll get an alert, but an attacker can bypass an entire system within 10 to 12 minutes in the enterprise world. So that's how sophisticated hackers are today. So now an analyst will look at an inference from a detection system, and then they need to quickly understand what's happening, right? Why is that alert? Are they going to look at individual raw data points from different other sensors to stitch it together? That's what's happening in the real world today, and they only have a short amount of time to duplicate it. That's why explainable inference is a problem. But now, in the context of neural networks, right? Like that's still seems to be an open-ended question. Like, what's the best way to embed explainable inference? Right? That's that's an open-ended question. But again, the problem is, explainable inference is a big problem within cybersecurity, also within healthcare as well. If you have an inference, someone needs to understand, okay, am I going to actually act on that? In which case, the inference has to be explained in a way so that it's easily auditable, easily understood by someone who's about to take an action on it. But perhaps you have some interesting ideas on how to make these models more explainable.
We have a interesting question/idea from Alice.
Okay.
Besides security, what if we use this as neural compression performance metrics?
Neural compression?
How many nads you get, like for a particular compression algorithm, or how stable compression is?
Did you mean compression?
Compression.
Okay. practically what the last experiment was testing.
That sounds like a very interesting use case. Yeah, that's a good use case thing.
Anybody else have discussion points they want to add? Yeah.
Just thinking out loud, but would there be value, say, you've got a model live doing inference in the real world, in like doing that nearest neighbor calculation on all the recent activation vectors to look for new states, like on the fly?
What problem are you trying to solve?
I don't actually know, but like, but then you could get like, okay, this is a state our neural network's never been in before. Like,
I think that's very cool. So in which case, perhaps if we reach a state, again, I'm just talking about, if we reach a state we've never seen before, maybe we can do some further investigation. Why was the state never reached?
Yeah, exactly.
Right, that's a good question. And then perhaps maybe that might be a high risk state as well, since we've never reached that state. We don't know what's going to happen. In which case, maybe we want to look into that.
Yeah, I'm thinking that would probably be valuable information.
I mean, yeah, that's a great question. That could be about. I mean, having that metric could be very important. Maybe that could be logged down, and then maybe from my understanding, I look at that. Usually, those states could be very uncertain by the model. In which case, maybe not enough training data was fed into the model. Maybe in which case, Bayesian a system like Bayesian neural networks could be used to kind of correlate that with the uncertainty as well. So now we're getting a different dimension. It's a state we usually don't reach, but maybe we're not even uncertain. We're maybe uncertain about the inference. In which case, that might give us more clarity as to what's happening. And then perhaps we can also do white box testing where you have different models, and then we kind of run different data points to identify those edge cases as well. And then once we have those edge cases, we kind of keep them aside, and then maybe we stitch them all together in real time using what you mentioned, but having these data points like maybe done periodically and then keeping them could be interesting. Okay, this is just my thoughts. This is still very new domain. I mean, but then there are various things we could even start and see where it leads us. Yeah.
So if anyone wants to do research with Tahseen, I think he's on the way. Does anybody have any other comments, discussion points? If not, go ahead.
I just have one quick question. I don't know if anyone's experimented with actually using TensorFuzz, but I'm just curious how it scales in terms of network size and input size. And I'm not sure if that was addressed in the paper, but does anyone have any insights or experience with it? No.
Well, I can give one example. From a coverage guided fuzzing standpoint, we are doing it in a distributed fashion in the real world today. Google already has an open source scanner which can be easily just deployed in the open, like a distributed environment. From a TensorFuzz standpoint, I don't know if the paper talks about running it in a parallelized fashion.
It does. You can certainly do it in parallel. Since the network's already trained, you can just choose a bunch of inputs, individually mutate them, and run them through. You're never changing the network, so of course,
no, you're not.
Yeah, it's fine.
Yeah. Did that answer your question? So,
it did. Well, then it shouldn't be a big challenge.
Yeah, you can do it in parallel. So.
Just curious about your thoughts. Like, if you use the fuzzing to find a bunch of NANDs in for your network architecture, so what are some of the ways for you to fix it? Like, do you change hyperparameters, number of layers, or add more regularization? Is there any ways to fix that? So I was just curious.
That's a good question. Perhaps we let the machine learning engineers talk about it.
Well, I'm not a machine learning engineer, so I think Vincent is. I know, that's a question I had too. Yeah. So yeah, if anybody has an idea, I'd be curious to know.
Yeah. So how do you guys solve it in the real world today?
Like when you find the network doesn't solve a certain problem, in terms, well, you have new input in this case, right? And then you just keep trying, I guess. We don't go deep into like the network itself, so we're just like, as long as it solve like the input that we have is fine. So we don't actually look at the architecture to change the architecture. We may add more layers, stuff like that, but not really innovating in that sense. So.
Just add the new data points.
So at the data point, and first of all, we don't really use a lot of neural network too, so that we don't really play with architecture that often. But if that does ever happen, I would just like try at the input in the training data and then try different type of solution too, and that's probably what I would do. Yeah.
So maybe we can also talk about the question you suggested with regards to why coverage-guided fuzzing with regards to neural networks should be hard, or else we don't get like a good scan. So that's a pretty good question.
This might be a minor point in the introduction of the paper, where
it's a great point.
More aimed at criticizing others' work, where their approaches easily cover in their coverage metric and get the full coverage very quickly. So probably the way, so all the network state is, we don't manipulate the weights. It is trained already, right? So all the network state is the inputs or all the activations values. In this paper, they look at activation values, which is totally fine. They look at them in Euclidean metric, which is an obvious case, obvious choice to start with. So it all sounds reasonable. They take all the available information and look at it using Euclidean metric and define some neighborhoods around test cases. So sounds reasonable, and they just point out it is reasonable and it is hard enough, so let's solve this problem first, because this might be the right way to go and the right lenses to view at the problem with. Yeah. So I guess it is clear now after the whole algorithm is discussed.
So they're only proposing one definition of coverage, and they laid out those several criteria that they wanted it to satisfy. Of course, it's not going to be the only definition of coverage that could possibly work. So I think it's open to interpretation, and if you have better ideas for coming up with coverage metrics, write a paper on it. It'd be interesting.
Yeah. And probably the first point of discussion might be why Euclidean metric.
Sure.
Yeah, maybe some points are better than the others and more sensitive than the others, some regions.
Okay, so anybody else? Okay, yeah, I'm gonna stop trying. Keep going.
I mean, we could stop. Well, I wanted to bring up the mutation step because it wasn't discussed very much in the paper or so far in our discussion. And it seems to me that the results of your fuzzing could greatly depend on how you choose to mutate at each step. They gave the example in this paper of strings of text where we change one character at a time, or image where we change one pixel at a time. And it seems to me that if you only ever did those very incremental steps, you may not get very far from your initial inputs in terms of how large input space can be. And also that if you're, for example, changing one character in a word, you will likely be going to non-existent words or incorrectly spelled words. This is something I was talking about with others. So I just wanted to get other people's thoughts on how important the mutation step might be.
So perhaps it is interesting to view at the interplay of the two parameters. How far we choose our mutant from what is already in the seed set, in the input set, and what is the distance L of the new result. So the acceptance of the result when we accept it and when we reject it. So these two parameters probably there is some interplay between them.
Yeah, but the mutation step is not just a parameter It's a much larger choice. Think of all the ways you could possibly change an image. So was there something particular about switching one pixel at a time that worked well? Or would there be other choices that are more effective?
I have a point here. Says from mutations, you keep on mutating over time, right? So the smallest deviation would give us the most like high resolution.
But input space can be extremely large. And if we only ever make very small steps, we would not cover much of input space.
But then we keep on. Okay.
But for images, it's like 10 by 10 pixels.
Yes.
Maybe with 10 levels of gray, you already have an input space which is 10 to the 100 big. And if you're making 1 pixel changes at a time, you don't get very far.
Then I have a point from a corner case standpoint, though, maybe it's just the small deviations which can lead to. So like these are the conditions we want to look at, right? So maybe it's if you maybe these could be identified only within small changes. Again, I'm just thinking about these small deltas could actually put us in these little buckets where you have abnormal behavior. So I mean, maybe you keep on changing, but you keep on changing over and over and over and over and over again.
Yeah.
Which leads to a larger change.
But then again, if we're making a very incremental change, we may not expect the activations to change very much. And so we may not find many incremental mutations which actually trigger our criterion of being outside the nearest neighbor L radius.
Are you saying it's not efficient?
I'm just wondering how important, what's really important here? Are we trying to explore input parameter space or activation space? I think we're more focused on activation space.
Yes. Just because our coverage is directly based on activation.
But potentially activation space might even be much, much larger than input space.
Yeah.
I guess it is related to the question that Alice is asking.
Yeah, Alice also asked something related. She's wondering if it would be more efficient to replace the mutation with Markov chain multicolor. Or is it the case that MC is not sufficient?
I haven't run. Yeah, but
I guess they did experiments in the paper to show that this fuzzing was more effective than a random choice from uniform distribution for one thing.
So you're mutating one thing at a time?
No, like randomly generating an input instead of pulling from your training set and mutating. Pulling and mutating was more effective than random generation. Monte Carlo.
Okay, so are there any questions from people who haven't asked a question yet? Maybe my coworkers in the back.
That could be a research. That could be a
Okay,
good
so
research.
if nobody who hasn't asked a question yet, I'm going to try to end the session for the third time. Because we're almost reaching 8:30, so okay, if there are any dying last questions, you can ask them now or just have Tahseen offline. Okay, if not, let's thank Tahseen, our speaker, Vincent, our host, Susan, one of our facilitators, and also me. I'm also facilitating.